Hello everyone, I'm Richard Faucheron, and I will talk about my PhD subject, which is the probabilistic forecasting of essential variables based on satellite image time series. So first we would like to do this propagation in time in the latent space of an autoencoder. So we needed to implement an autoencoder, so this is what I'm going to present you here. So I'm also, this work is also within the RELEO chair. So Julien talked about it before, but just a quick recap. This RELEO chair aims at implementing a model that can handle any kind of Earth observation data as input, so from satellite images to in situ measurements, to provide essential variable maps. And all is trained in a self-supervised way and guided with physics. And my PhD subject, so there are several PhDs which are working on this model, and my PhD subject focuses on the latent space, which has to be probabilistic, and then we will have to propagate it in time. So for the autoencoder, we based our model on two architectures. The perceiver, which allows us to take as input any kind of data configuration, in the sense that we explode the data into its pixel elements, and we create a sequence of pixels. And for each of these pixels, we associate acquisition context, so an embedding of different information, such as the acquisition date, the spatial coordinate, resolution, etc. And the second architecture is the variational autoencoder that you probably all know of, which allows us to have to provide an uncertainty in the latent space, but also in the output of the model. So the decoder can directly produce both the best estimate and its uncertainty. So we continuously improve this autoencoder, but we ask ourselves, when do we stop? When do we consider that we have a variational autoencoder that is good enough, such that then we can use it to work on the forecasting tasks? So to evaluate this variational autoencoder, we listed some criteria, and here I will present you 4 of them quickly. So the two first are that we want a variational autoencoder that is able to capture the essential features of the input data as well as their dependencies. So since we have a very weak decoder, we can consider that the essential features are captured if we can reconstruct the main patterns of the input. So the idea is not to have the perfect images, but simply to have a reconstruction that show those patterns, those main structure. Also, as for the dependencies, we can mask during the inference some part of the data, and if the model is able to reconstruct those missing area, then it would show that the model is able to use the remaining information to fill the gaps. And here the two last criteria are about the latent space. So we want a latent space that is large enough to encompass any important features, any important information, but as small as possible to avoid having latent variables that would not provide any information and would be then useless. So here we have computed the statistical dependence between each latent variables and the input data. So here in blue, and we want to have the highest dependence for every latent variables. So we see that the majority of the latent variables are effectively used and convey information about the input data. But then the question was, is this information the same? And all latent variables would share the same information, so there are a need for low redundancy in the latent space. So this is what we computed here in green, where we compute the dependence between each latent variables to ensure that this is not the same information that is shared. And this is it. So we have some criteria that we have checked with a model, and now we consider this model to be efficient, and we will use it for the next forecasting task. Thank you very much.